Welcome everyone to the MagNetZ seminar. So I'm really happy today to have a collaboration with the Latin Mag series of seminars and community. So the presentation today is by Romina Achaga on paleomagnetic and paleoenvironmental changes in the Barrancosa Lake in Argentina over the last millennium. And Romina is a visiting postdoctoral researcher at the IPGP and also affiliated with CONICET in Argentina.
Okay, so good afternoon, everyone, and thank you for the invitation and this collaboration between MagNetZ and Latin Mag Talks. Well, as Anita said, my name is Romina, and today I will be presenting paleomagnetic and paleoenvironmental changes in La Barrancosa Lake over the last millennium. And so, no. So as you know, I wanted to do a brief introduction about paleomagnetism and lake sediment. Lake sediment are a very valuable archive since they are continuous record of the geomagnetic field variations. So when the magnetic grains like magnetite settle through the water column and pass into the sediment column, they align with the Earth's magnetic field and retain a remanent magnetization that then we can study. So we go to the lakes in general with different kind of coring techniques, and we recover these sediments using different corers, but in general we don't preserve the orientation of the core. So we lost the absolute declination, and we have but anyway, we have, as it is a continuous record, we can still have the relative variation of the declination, also the relative paleointensity and its inclination. And depending on the length of the core and the sedimentation rate in the lake, the sediment cores can span time scales between several hundred years to over 1,000 years. But in this study, we will focus just in the last millennium. So the La Barrancosa Lake is in an area called Pampean region in Argentina. It is in the central Argentina, and it is characterized by fertile soils and a large number of very shallow lakes, which are very sensitive to climate change. There are many or some studies in this lake sediment for environmental changes, but there are not many studies in paleomagnetic variations during the Holocene using lake sediment. So there are mainly two main reasons to study this area. And the first one is that it is within the South Atlantic Anomaly, which is one of the most remarkable features of the Earth magnetic field today. So it's very important to have more paleomagnetic secular variations study in this area to track the South Atlantic Anomaly. But also related to the paleoenvironmental reconstructions, it's a very important area to have high resolution study during the last millenniums, since it is one of the most productive agriculture areas in Argentina nowadays. So it is under an extensive land use change. And this makes that studies in this area are very, very useful to put in context how the recent environmental change can be seen from a millennium or centuries scale perspective. Also, I wanted to show you this map from GeoMagnetic database that shows the global distribution of sediment cores that document paleomagnetic field variation during the last 50,000 years. And as you can see, most of the records are from the northern hemisphere. So this is showing that there is a clear lack of data in southern hemisphere, and it gives another reason to continue studying this area. In particularly La Barrancosa, it's one of these shallow lakes that I told you in the Pampean region. It's located in the southern part of this area. It is a closed basin lake, with a maximum depth of 5 meters. And it is surrounded by these low cliffs that I show here in this picture in the north part of the lake basin, with a transition into aeolian deposits on the other side of the lake. And in the recent time, the intensification of the agriculture in the area, as you can see in the map, it is full of fields that do agriculture. It's very intense in the last decades. So we previously worked at La Barrancosa during 2022 when I was doing my PhD in collaboration with all these co-authors. And we recovered 3 short sediment cores of about 60 centimeters long that were previously studied for paleomagnetic and rock magnetic analysis to make paleoenvironmental reconstruction too. But the age-depth model was uncertain since there was a big change in the sedimentation rate, as you can see in the age-depth model here. The inconsistency was between the radiometric dating on top, the plumb dating on top, and the radiocarbon date that we did on the base of the core. To validate the upper chronology, the plumb chronology, we used the cesium well-known marker and other regional markers, and there are 2 organic rich markers in the Pampean region that were studied previously by other authors. We found them in La Barrancosa too. So this validates the upper chronology. We thought at that point that the radiocarbon dating might be affected by carbonate contamination. The sedimentation rate proposed by this change in the sedimentation rate was that from 40 centimeters to 60 centimeters, we have a sedimentation rate of 0.2 millimeters per year, which is very low for the compared with other records of the area. So despite these problems with the chronology, we did the paleomagnetic measurements, and we had very good behaviors in the samples, as you can see in this side of the plot. There was a very stable characteristic remanent magnetization that we could calculate the direction for all the samples. And when we compute the mean inclination for the 3 cores with the standard deviation, and we compare with the geomagnetic field model for the sites, we saw that the inclinations were higher of what we would expect for this time period for this region. All the samples gave inclinations that were higher than -45 degrees. So this was reinforcing the idea that there was a problem with the chronology and with the radiocarbon data at the base. So at this point we said, okay, we need a longer core and we need to keep on study this site. So we decided to go again to the field. Last year, during my first year as a postdoc, we returned thanks to a founding of Earthwatch. We went and we used for the first time this platform with the Usinga core, and we could collect 90 centimeters long core, which obviously we aim to go deeper and take a lot of meters, but unfortunately we hit a hard rocky layer that we couldn't go through even using a motor hammer. But it was anyway the longest core from this lake so far, and it was also an important step for us for the group to use this instrument. This was also a great opportunity, the one that Earthwatch gave us, to make not only the sampling, but also an educational project with a high school student from Chishire School that came to the field. So we did this sampling together, and we also work with La Barrancosa sediments with them. We got this core, we brought it into the lab in Tandil, we opened it into half, and we performed the lithological description, magnetic susceptibility. We measure magnetic susceptibility with a spot sensor. After that, I brought the core to Geopolar in University of Bremen. We carry out there the XRF core scanning to measure the elemental composition in 1 millimeter resolution. And after that, I subsampled this half of the core in 1 centimeter resolution to make measurements of total carbon, total nitrogen, total sulfur, and also after acidification of these samples to measure organic carbon, and after that to calculate the inorganic carbon. And on the other half of the core, we subsampled with 8 cubic centimeters boxes, plastic boxes, and we got 38 samples that I brought to Instituto Nacional de Geofísica y Vulcanología in a short stay I have there to make all the rock magnetic and paleomagnetic analyses that I describe here. We also perform a new radiocarbon dating on the bulk sediments because in this course, I didn't said that before, there are not plant remains. So when you don't have macrofossils, the radiocarbon dating is more complicated if you have carbonates in your core. So as we had this problem, we decided to do first the geochemical analysis before going to the radiocarbon dating. And we saw it visually, but with the analysis, we corroborate that there was organic rich level at 65 centimeters that has a low inorganic carbon. And we decided to date this layer and not the base of the core, where you can see that the inorganic carbon is higher than the organic carbon. So we additionally found the 2 chronostratigraphic markers, the rich organic layers that I showed you before in the other course, chronostratigraphic markers. And the new bulk radiocarbon date at 65 centimeters gave an age of 1,400 and 1,600 calibrated years of the common era, which gave us, when we built the age-depth model, sedimentation rate of about 1.2 millimeters per year and a basal age of 1,300 years of the common era, which was more consistency with the chronostratigraphic markers. So this highlights the difficulty of dating lake sediment when we don't have macrofossils and we have carbonates. So once we have the age-depth model, I can go on with the lithological and rock magnetic results. In general, the core was composed by silty clays, and we identified 3 different lithological units in Unit 1. But Unit 1 was composed by silty clay mud with a massive structure. And in Unit 2, it was also composed by silty clays, but it has interbedded fine sand layers in the middle. And there were also some banded layer that suggests that there were different depositional conditions within this unit. And Unit 3 is the one that has more fine sand contents than the previous units. About the rock magnetic results, we can see that there is a general trend to an increase from base to top. In general, Unit 3 was very stable. There are not much changes in Unit 3, but Unit 2, you can see that there are variations in the magnetic mineral concentrations and also in the magnetic grain size. And also there are differences between the remanences and the magnetic susceptibility, which might suggest that there is variability in the magnetic particle assemblage. And then Unit 1 that shows an increase from base to top. More concentration of magnetic minerals toward the present. About the magnetic mineralogy, we have here the S ratio that presents values above 0.9, which suggests that there is a dominance of low coercitivity minerals. But there is a slightly lower values in unit 3, which might show that there is a minor secondary contribution of higher coercitivity minerals along the core when we see these slightly lower S ratio values. So to further characterize the magnetic assemblage, we use this plot, the Peters-Deckers plot, that suggests also the presence of magnetite or titanomagnetite, and the Thompson and Oldfield diagram that was used to infer the magnetic grain size, showing that unit 1 and unit 3 don't show much variability, but unit 2 show a loss of variability along the unit. We also did a hysteresis loop for all the samples, and they all are like the one I'm showing here. They were very similar between them. And they are very narrow loops that are typical behavior of pseudo single domain magnetite or titanomagnetite. And we also perform some thermomagnetic curves of magnetosusceptibility versus temperature that shows a decrease between 570 to 610, which is consistent with the presence of magnetite or magemites. And there is also in some samples, not in all of them, but a minor component near 680. Well, the decrease is between 600 and 680, which might indicate that there is a minor proportion or a low proportion of hematite along the core. But in general, I wanted to show that there was a very stable magnetic mineralogy, but then the magnetic grain size was a little bit more variable within the core. Also, we performed the IRM acquisition curves, and for all the samples, the saturation was reached before the 300 millitesla field. The curves were also analyzed with the Max and Mix program. To identify a magnetic component with different coercitivities, and the result shows for the samples in general that there is a principal low coercitivity component and a secondary minor high coercitivity component. I put 2 different samples, one from unit 1 and another one from unit 2, because they show some small differences, but you can see that in unit 3 there is a higher relative contribution to the magnetization of the second component that suggests that there is a slightly greater presence of high coercitivity minerals in this unit. So after the characterization of the rock magnetic of the rock magnetism, I can continue with the paleomagnetic results that we found in this core. As you can see, the characteristic remnant magnetization show linear trajectories toward the origin with well-defined direction. We could calculate the direction. All the samples were very similar and very easy to analyze and beautiful. Since the core was not oriented, we centered the declination values around 0. The inclination ranged from -64 to -17, which is consistent with the for these latitudes, consistent value for these latitudes, and the maximal angular deviation was below 5 degrees for all the samples, showing that the high quality of this directional data. So based on this HDET model and the new paleomagnetic data, we reconstruct the paleosecular variation for the last 700 years, and we compare our directional result with the geomagnetic model, different geomagnetic models, that for this time period showed quite agreement between them. and they align much better than in the previous work in 2022 with this new HDES model. And we also compare our inclination curves and declination curves with the stalagmite, with the work on a stalagmite in Brazil that show the inclination show a good agreement, considering that they are not close. They are the stalagmite in Brazil is further north, but this study is one of the best data, and it's a very good high resolution paleosecular variation for South America. And I also compare my results with other Argentine paleosecular variation records, but they have a lower resolution for this time period. Most of all, there are not much data for the last 500 years. So after the paleomagnetic result, I also wanted to show you how we did the paleoenvironmental analysis. And for that, we cannot use only the rock magnetism, but we also need other proxies. In this case, we use the geochemical result. I am showing here some of them. I didn't put all the elements, but the most important ones. So the idea was that once we have the chronology, reliable chronology, and we know that the core was more or less 700 years, we knew that we might find there how was the little age in the Pampean plains. And it's very interesting to study this event because it's very well known in Europe, for example, but there are still some studies and controversial about how it was in different regions of the southern hemisphere. So, for example, we use the iron and titanium profile as indicatives of the detrital input in the catchment area. We also use the inorganic carbon and the calcium titanium ratio, reflecting the carbonate content, which depends on the evaporation and the salinity of the lake level. So when we have high calcium titanium values, we have in general low lake level. We also have the organic carbon and the nitrogen reflecting the nutrients and the lake productivity and the organic matter on the lake. So with all these parameters, we start analyzing what happened with the paleoenvironmental changes. And as we see in the unit 3, we observe that there is very low TOC, organic carbon and nitrogen values, suggesting that the productivity of the lake was very low. And at the same time, we have high calcium titanium ratios and inorganic carbon values that suggest that there were drier conditions in the lake that might correspond to the first pulse of the Little Ice Age. Then follow this dry period, we have a very sharp increase of the organic carbon and the nitrogen, which indicates that there were good conditions in the lakes for the lake productivity. And after this peak, we see that there is a first humid period during the Little Ice Age with also high TOC values and nitrogen values, which show us that there was a warm and wet period during the Little Ice Age in this region. After that, after this humid phase that ended at the beginning of the 18th century, we go again to another dry period, which is like the second phase of the Little Ice Age, and it goes until 1830, more or less, which would be the end of the Little Ice Age in this area, since we saw after that that the productivity in the lake started rising again until 1970, where we have another increase in the lake level that it reflects the conditions, the environmental conditions we have now in the lake. So studying these paleoenvironmental variations, it's not only good to have the environmental reconstruction in the lake, but for people studying paleomagnetism in this sediment course, it is important because it might these environmental changes might affect the study of the relative paleointensity estimation. So to understand what happened with the paleoenvironment and try to analyze how the rock magnetic properties change, it might give us a clue when we see strange changes in the relative paleointensity. So for example, in this core, we have difference in the base of unit 2. We have a difference between iron and titanium groups that might reflect that the iron is influenced by different processes inside the lake, like dissolution, but also could be autogenic precipitation of iron. And these processes might give us a change in the magnetic signal that might give an under or overestimation of the relative paleointensity. And in this core, when we see this change, is when we saw the change in the magnetic grain size, this peak in the magnetic grain size in the base of unit 2 that we can see in the relative paleointensity when we studied. But this is something that we will analyze in the future, and the idea is to see if we find another approach to reconstruct the relative paleointensity in this lake. Also, to connect the rock magnetic variations with the paleoenvironmental, the geochemical data, we saw that we could associate the wet periods, the most recent one and the one within the Little Ice Age, with a higher concentration of low coercitivity magnetic minerals. It happened in the two pools, wet pools. And also in the driest phase in unit 3, there were lower magnetic mineral concentration in general, and also there was a higher contribution of the higher coercitivity component. And the identification of these wet pools and dry pools, it was very interesting because it was aligned with historical and archaeological evidence in the area. So we revised archaeological and historical articles from central Argentina that shows that there were 3 different phases during the Little Ice Age. They describe 2 cold and dry phases. The most recent one has very good agreement with our results. And they also identified this warm period in between the Little Ice Age, which is very consistent with our record. And all this information comes from observations for example, in archaeological study, where they detect that there were changes in the how the people were storing the food, and there were changes also in the vegetation. And during the wet period, there were different studies about the maps of that time that shows how the rivers, and there were major flood in different rivers or lakes, and the same with the documentation that showed that during the 18th century there were extreme droughts in the area. And also there are other lake records of the region that show that the final stage of the Little Ice Age was marked by a very dry condition during the 18th century. And after that, the lakes gradually recovered the higher level between 1850 and until 1970, when we have this very wet period that is connected with the nowadays environmental conditions in the area. So the conclusions are that we developed a age-test model for the site, comparing with the previous studies. That with this we enhance the paleoenvironmental and the paleomagnetic interpretations in the lake. So we provide this new high quality paleomagnetic record from La Barrancosa Lake, directional record. We also could study the environmental variations that indicate that there were a lot of, alternance between wet and warm periods and dry and cold phases. It is very well defined, the little ice age. And the most important thing is that I would like to use this opportunity to say that these multidisciplinary and multi-proxies work are very necessary to make good interpretations of not only past environmental changes, but also about our paleomagnetic records. I also wanted to show you that I continue expanding this work to other lakes across Argentina and Brazil, and this include Lago Ñeloán and Lake El Desierto and Lake Alecho. And Lake Alecho and Lake El Desierto were sequences that I recovered in my recent visit to University of Bremen, thanks to the collaboration with Professor Solisca. And I think that these records are really valuable data to reconstruct paleosecular variations in South America during the Holocene. So these are all the references, and I would like to take a minute to thank, first to Earthwatch for the funding, and also in general to international collaboration, but for my research grants in Germany, and also to the transnational program of ILGE that allowed me to go to Rome to make the paleomagnetic measurements. And also I would like to thanks to all the researchers that were part of this study, especially to Claudia and Alicia, that are my colleagues in Tandil. And I want to thanks also to CONICET and my public university in Tandil, which I am part since I am a degree student. So thank you so much. And if you have any questions, I will be happy to answer.
Thank you very much, Romina. Let's all give a big round of applause. Very interesting presentation. Very nice talk. Thank you. Okay, so Hakan has a question in the chat. I will read it. Thanks a lot for this nice talk. 2 questions. If I saw correctly, ARM and SIRM values are decreasing from unit 1 to unit 2. Vice versa for ARM ratio over SIRM. This is the opposite for ARM versus SIRM ratio. This is quite interesting, as one would expect both ARM and the grain size ratio to decrease downwards from the lake bottom by a dissolution of finer grains. What could be a possible reason for that? Have you tried any fork? Did you try to check if there is any correlation between rock mud parameters and the RPI, the relative pole intensity?
Yes. I knew that something of this would come. We don't have the possibility to perform forks for this study, but I also tried to, let's see if I can show you, no. But at this time, we are studying the relative paleointensity, and I want to show that it was still not possible to isolate the environmental contribution. And this big peak, even though we see that there is a decrease from base to top, which is when we compare with archaeomagnetic data, for example, it is what we expect for this time, a big decrease between the 17th century to the recent time. But there is this conspicuous peak. There is just happening when we have this change in the magnetic grain size. So at this point, we are, as I said, still studying what is happening with this, and if there is any way to isolate the relative paleointensity and try to take out the environmental contribution. But yes, this is very interesting. I was not just trying to analyze the rock magnetism, but also to combine it with understanding environmentally what happened, and to see if there is a way using elements or also the CNS results to see if we can do something to recover the relative paleointensity, which is what is good is that we know the environmental context and we might continue working to see what we can do.
Thank you. We can tell you we're ready for this. Any other question from the audience? Yes?
Yes. Hello. I am not DJ Aula 01. I am Augusto Rapalini from Buenos Aires.
Augusto.
Hello, Romina. Nice to see you. A very nice talk. Congratulations. I have a couple of questions. You show a very, very nice trend of shallowing of the inclination in most of your core. That matches very well with the Brazilian record in the stalagmite. That seems very robust. I have a question with the last few samples that show a sudden increase in the inclination. Do you think that's real or maybe an artifact?
Yeah. I mean, what I can say is that the samples behave really well. They are all, as I show in the Seidelberg diagrams. But also we have a change in this unit 3 of that I said there is I'm trying to go back. Yeah, and there is also a slightly change in the magnetic mineralogy and also in the assemblage, in the magnetic assemblage. But I thought that this might affect obviously the relative paleointensity, but the results were good, so I include them. And obviously I say, okay, I would like to go deeper. I want to get more, but to see what happened there. Because to analyze just the last part without knowing what's happening afterwards, it's difficult.
Okay. And also a question about the filling of this sediment or the deposition of these sediments. It seems that you have an abrupt change of sedimentation rate in the last decades, isn't it?
Yes. One thing that I didn't say, because to explain what happened in the field, and that in this new core, as we have a new core, we lost the first 10 centimeters because we have the piston in this core and we had to extrude the core. So the first centimeters, we lost it, but we have it in the previous study. And in the previous study we see that there is an increase, very high increase in the sedimentation rate during the last 3 decades, that we are thinking if it might be related with the agriculture activities in the area. And there are also other we didn't study in this core, but in the previous one we saw that there are we measured the heavy metals, and we saw that there is also an increase in the heavy metal that could be related with the agricultural activity, but we are still studying that. So what is good is that in the previous core, we have like the most recent, the last century that we can study very well. And now we could extend this study to the Little Ice Age with this new core.
Thank you, Romina. Congratulations again.
Thank you, Augusto.
Thank you. We have a question from Sanya.
Hi, you hear me well?
Yeah.
Thanks for the nice talk. Great to see that there are new records coming from that region. I have a couple of questions. First is, I know of a couple of other records from the region. I mean, probably more older studies. Have you do some comparison with those? I mean, I don't have the names now on top of my head, but
I have them here because I put I didn't want to put a lot of information, but as I said, there are other Argentinian records. These are all the records we have, and I compare with all of them. The order is with different latitudes, so from north to south. And as you can see, there are the inclination, we could say that considering the difference of latitudes are quite similar or have a similar trend at least, but we have difference in the declination. So my idea about showing this is also that we need to continue getting these continuous records like stalagmites or sediment cores that might help us to understand better what is going on in this area. I mean, to be able to study the South Atlantic Anomaly and what happened with it during the Holocene and so on, we need more data in this region. And actually, for my core, it is, I mean, I have to compare it with something else, but there is not something else around. So we still need to continue working and adding more records from this area.
Can I just continue?
Yeah.
The questions. Yes, so you said for declination you don't have the orientation and that's relative, but I assume because it's so recent you can kind of orient the top of the core and probably the rest, right? To get the absolute. And just to comment on the models, because I'm on that side a little bit. There's few more recent that you may want to consider from last year or the year before, like.
Oh, good. I try to consider many of them. Also, for this period, there is quite an agreement. But when we go to the past, and not to very old times, I mean, when we arrive to 4,000 years before the present, we start having differences between the models, and yes, I will try with the new ones. Sanya, thank you.
Yes, you're welcome. Thanks a lot for your answers.
Thank you. Any other questions? It was a very nice and exhaustive talk. You explained a lot, and you were also already with all the questions that come. Yeah. I don't see any other question. So
good. We can go to the good part.
Yeah, so thanks again, Romina. Let's give Romina a big round of applause. And yeah, see you the next MagNetZ.